Hi, everybody. Welcome to the AP Environmental Science Virtual Classroom. I'm Ms. Fassler, and I teach APES in Marshfield, Wisconsin. So if you did the live lecture with Dr. Sowell last week, you didn't have any homework. It was No Homework Friday. So just a quick overview of your exam. Haven't seen this before, have you? Our two questions that we'll be writing on May 18th. And then a reminder to check out the College Board Tips for Open Note tests. Really encourage you to do that. Dr. Sowell and I will be throughout this week of review and during our practice exams, we'll really be trying to get you to hone in on visualizing what that exam day is going to look like and what it's going to look like to sit down with all of your notes in front of you and helping you organize that. So today, last week we spent almost the whole week on Unit 5. Lots of information in that land and water and human impacts. This week we're going to spend 3 days looking at energy resources, and I'm going to do the first 5 learning targets there. Dr. Sowell will pick up tomorrow with renewable resources, and then we'll have a third day for wrap up. Obviously, in this kind of introduction, and we'll dig in a little bit to fossil fuels, we really focus in on big idea number 1 on energy transfer. Energy conversions underline all ecological processes. So we saw this recently in the review when we looked at the 10% ecological efficiency rule and how energy is transferred from one trophic level to another. Well, in this unit, in Unit 6 on energy resources, we're going to look at energy systems that take energy resources and put them into usable form of energy for us, but we still have to look at this second law of thermodynamics. There are 3 big objectives I have for today then. Describe how patterns of energy consumption differ throughout the world. Explain why the availability of natural energy resources depends on a region's geologic history, and justify the use of different energy resources based on economic, ecological, and human health factors. So we're going to start right away with this discussion of global energy resources, and we're going to focus in on this essential knowledge statement that the geology of an area determines where fossil fuels are located and which fossil fuel that is, if I have coal, oil, or natural gas. Let's see if we can kind of simply go over a description of how those fossil fuel resources got there. They're fossilized fuels. So they're all of the organic matter, hydrocarbons present from once living things like plants and algae and plankton that were drifting in these shallow seas millions and millions of years ago. They died, they sank to the bottom of that ocean sediment, and then over that millions of years, millions of tons of sediment all accumulated on top of those hydrocarbons, the carbon remains of those once living organisms. And we had these great conditions of time, for sure, millions of years, hundreds of millions of years, and heat and pressure, and different locations on the planet had kind of different heat and pressure conditions. That means that I had different kinds of fossil fuels form in different places. And that determines if I had coal, oil, or natural gas. We don't need to dig into these 2 maps and do a whole lot of interpretation. I just want us to make sure we can see some type of pattern of where these fossil fuels are located. So the top map here is showing me major coal deposits around the world. The bottom map is showing me major oil and gas deposits. And I can see that there's definitely a pattern, that fossil fuels tend to be located in kind of the same areas. And there are some areas that have a wealth of fossil fuels and some areas that have little to no fossil fuels. So let's just take one quick little check-in here on that idea of how the geologic processes of time and heat and pressure determine the location of fossil fuels. During the Cretaceous period of Earth's geologic history, Montana was covered with lowland swamps. The plants were buried and slowly decomposed. Which of the following resources would most likely be mined from the plant remains buried in eastern Montana during the Cretaceous period? And the answer is fossil fuels such as coal. Yay! So let's take that idea of how long these fossil fuel resources took to form and review the idea of renewable versus non-renewable. I think it's a pretty easy concept. So I'm going to have you determine if the following statement that I'm going to show you in just a second is an accurate description of the difference between renewable and non-renewable, and justify your claim. Renewable resources are those that cannot be used again and again, whereas non-renewable resources can be reused. So think about that one for a minute. Is that accurate or inaccurate? And justify your statement. So the key word in this description here is really this idea of being used or reused. I would say that it's an inaccurate description. Look at the terms, the vocabulary that I want to have on my note sheet to describe a renewable resource. It can be replenished or resupplied or replaced or reformed naturally at a rate at or near the rate of consumption. So remember, we talked about sustainable use of forests and wood as a fuel, and we'll look at wood again here in a minute. That is a renewable resource. I can't use the wood again. Once I burn it as a source of energy, I don't have that same energy source, all of that cellulose and those hydrocarbons that I can burn to release energy, but I can grow more trees. Whereas a non-renewable resource, the key term here to describe this, these are present in a fixed amount. The processes that created them require very long time and those conditions of heat and pressure that once they're gone, they're gone. They are present in a finite or a fixed amount. Let's dig in a little bit deeper to non-renewable resources as we relate it to our big idea on energy transfer. So here's a model that shows the equation, the balanced equation for the combustion of methane. Methane is a fossil fuel. We're going to look at natural gas. That's the main component of natural gas. And we'll look at that in a couple of minutes. But I can see from the balanced equation that the same number of carbon, hydrogen, and oxygen atoms exist on the reactant and the product side. After I combust that fuel, I still have the atoms. Those atoms can be reused, you might say, because I can take that carbon dioxide and a plant can take it up in photosynthesis. But I'm never going to have more methane to burn. I'm never going to have the conditions on a human time scale that can put those atoms of carbon and hydrogen back together as a fossil fuel that I can extract and burn, because of the conditions that created that methane to begin with. So as I convert that methane into different kinds of compounds, even though the atoms don't disappear, the amount of usable or high quality energy is diminished. I want to take a minute and talk about the equation itself. And one of our big concerns about using fossil fuels is the disruption to the carbon cycle. We take these fossil fuels that are carbon stored in massive amounts, that's been down underneath the ground for hundreds of millions of years, and we are extracting them and burning them and putting that carbon as a form of carbon dioxide into the atmosphere. Carbon dioxide is a greenhouse gas. There's no complementary process that takes that carbon out of the atmosphere at the rate that we're putting it in through burning fossil fuels. It's true that photosynthesis removes carbon dioxide, but the process of photosynthesis and cellular respiration are in a balance, are in an equilibrium. We keep adding more and more and more carbon through the combustion of fossil fuels that normally wouldn't be carbon that would be in the atmosphere. What about renewable resources then? Do we still have the law of conservation of matter here? Well, in photosynthesis, this is an energy process. I can take atoms of molecules of carbon dioxide, combine them with water, and form sugar and oxygen. The difference is that I'm going to continue to recycle those atoms of carbon. The sun comes up every day, and I can do this process of photosynthesis again. So the carbon dioxide that I took out that was converted into a sugar is going to be eaten by an animal. That animal is going to do cellular respiration and put that same carbon dioxide back in the atmosphere. Photosynthesis and the reverse of it, cellular respiration, keep that concentration of carbon dioxide in an equilibrium. We're going to look at biomass fuels and come back to this idea in another section on energy. So we've established that there's this uneven distribution of fossil fuel resources. The geologic processes that created them means some areas of the world have a lot, some of the areas of the world have none. Well, we can see patterns of consumption as well. This map is showing me color-coded, the light colors, yellow and orange, all the way up to the dark red. That's the amount of energy that different regions use. And I can see a pattern emerge where it appears as the developing countries don't use nearly as much energy as a developed country does. And that makes sense if we connect this to the idea of the demographic transition model and what happens as a country goes through the process of being industrialized. Let's take a look then at a question that there's often a misconception about this when we see questions about per capita energy use on the national exam. So I want you to see if you can describe and compare total resource use per capita between developed and developing countries. And I'll give you a minute to think about that one. So one of the biggest misconceptions students have, and it's pretty clear when we read the way they respond to a per capita question, is that a student might say something like, well, countries that have really big populations have a greater per capita energy use. Per capita means per person. It has absolutely nothing to do with how many people there are in a country. I can have a country with a very small population overall, but a very high per capita resource use. So the first thing they wanted us to do here is describe and compare, come right out and make a statement of claim that developed countries use a greater amount of resources per capita than a less developed or a developing country. And then 2 points for comparing them. And I could do one or the other. So I could say, well, developed countries have a higher standard of living. They have a high gross national product. They have more money to spend on luxury items, which require a greater use of energy. You could even have stated actual statistical values about how the population of countries is kind of split 20-80. 20% of people live in developed countries, 80% in developing, yet the resource use is flipped. 20% of the population uses 80% of the resources, therefore the per capita, the energy used per person is much greater. Notice you could also have talked about the type of energy used. We tend to use fossil fuels in the developed world, whereas in the developing world, they use biomass or a more low-tech fuel. And that'll make more sense when we review the process of extraction that is required to get a lot of the fossil fuels that we use. This is a graph that is showing me global fossil fuel consumption. You would probably recognize that if I went back before the Industrial Revolution, wood or biomass would have been the major source of energy. This is then from the Industrial Revolution on, the number of terawatt hours. It's a measure of energy consumption. And we can see that after wood, coal came on the scene and really fueled the Industrial Revolution. Coal was replaced primarily by crude oil, which more recently has largely been replaced by natural gas. But the bottom line is that as a country becomes more industrialized, their demand for energy increases. Their total demand and their per capita demand both go up. And the majority of that energy to fuel the industrialization of many of those less developed countries is going to come primarily from fossil fuels. That's concerning to all of us because of the implications of the amount of carbon dioxide being added. So we've been talking a lot about all these fossil fuels we're using, and we're using more coal, more oil, more natural gas. What determines which natural resources we use for energy? What the factors go into that? Well, the first is availability. How much of that resource is there? Where's it located? Is it easy to get? Do I have to build an offshore oil platform that's a couple hours flight from the mainland? Or can I erect an oil well and pump oil right out of the ground? Can I put up a windmill and get kind of energy just by letting the wind turn a turbine? The availability and how easy it is to extract and process and transport is a big factor in our energy decisions. Government regulation also plays a big role. The government can either incentivize or disincentivize the use of certain fuels or our rate of consumption, and they do that largely through taxation. We're going to come back to that in a second. Remember that idea of full cost pricing? If I want to disincentivize the use of fossil fuels, which have all these negative costs associated with them, I could increase the price of that by taxing those fossil fuels that have all the negative problems associated with them. There's fossil fuel subsidies. You may have heard of subsidies in a number of different applications, but certainly some of the biggest subsidies are for the fossil fuel industry. A subsidy is some type of government action that lowers the cost of energy production from fossil fuels. It could be a tax incentive. It could be funding for research and development to build that offshore oil platform and find new sources of oil on the ocean floor. Maybe it's simply saying, here is federal land that belongs to all of us. We're going to let fossil fuel companies go onto that federal land and extract those resources, maybe for nothing or for a very low cost. All of these factors determine the price of a certain fuel, and price determines to a large extent our energy decisions. I want to take a minute and clear up another misconception that we often see in the writing of free response. When a student has to ask about a solution or a strategy to reduce the use of fossil fuels, they might say something like, well, the government can raise the price of gasoline, and then people won't use as much gas and we won't have as many problems with combustion of gasoline. People will use less. Understand that the government does not set the price of that fuel. The price is determined by the market. Right now, gas is about as low as it could possibly get. That's because with the pandemic and industry shutting down, there's just not a market for all of that oil. So there was a lot of oil on the market. They didn't even have a place to store that oil anymore. So they have to let it go at a really cheap price. The government does not determine the price of oil. The government can determine the price that I pay at the gas pump by heavily taxing or not heavily taxing what I pay for gasoline. All countries are buying oil on a global market. The difference is some states or some countries may want to reduce the use of fossil fuels and apply a heavy tax. Likewise, some states or countries might want people using a lot of that energy and would have a low tax on it. Let's take just a step back for a minute and look at a couple different types of fuel before we go in the detail on fossil fuels specifically. And we talked a little bit about fuel wood already when we were talking about forestry, and I mentioned charcoal. I think I may have shown you that same picture. These terms, fuel wood or charcoal, kind of all mean the same thing. It's a source of energy that is used for people in much of the developing world. It's often the only source of domestic energy they have for cooking or heating or boiling their water. But there's a lot of negative consequences associated with this process, especially when those fires are burned indoors or in a very poorly ventilated area. We're going to come back in the latter part of the week when we look at air pollution, and we'll talk about that as well. One of the solutions that some nonprofit groups are working with people in developing countries to try to provide them with a chimney or some type of ventilation system, so that they can reduce the exposure to women and children to some of those indoor air pollutants. So we'll wrap back around to that in a little bit. In general, wood can be used in a developed country as well, probably more in rural parts of the country where people might actually have an outdoor wood burning furnace, not just a fireplace in their living room. This might be the only source of heat for some people, but they can put big logs, a sustainable source of fuel, into that, and then that heat is piped into their home. You may have heard of a wood pellet. This is a picture of a wood pellet stove, and it's indoors, but again, it's got a chimney and it's vented. And it's kind of a great use of many of the waste products associated with logging. I can take even sawdust from construction and I can compact it. It looks kind of like little animal poop or rabbit poop, like little rabbit pellets, but I just buy it in big bags and I put that in my furnace and light it on fire. We can also make those pellets out of things like palm kernel shells or coconut branches, anything discarded during that logging process. And again, if we can start transitioning the developing world to some sustainable uses of a renewable fuel like this, that's really our goal as they start to get more developed and use more energy. So what about those fossil fuels? Let's start off with coal. You probably remember hearing about anthracite, bituminous or bituminous coal, and anthracite, bituminous, lignite, and peat. Peat really isn't a form of coal. It's this deep brown kind of soil deposit that's partially decomposed vegetable matter, and it forms in wet, often very acidic environments, conditions like we would see on a bog. I think these are a couple of guys with their little dogs watching them here in Ireland, and they're digging out that peat. That peat will then be taken back and burned, could be in open fire or in more of an enclosed vented fire. We often dry that peat and sell it in a gardening center like peat moss. Remember that this anthracite is the most desirable form of coal. Back to that idea that all these fossil fuels formed under conditions of time and heat and pressure, but what form of coal I have depends on those geologic conditions. It's the most desirable because it has the highest heat content, lowest sulfur content. Remember, coal's got a lot of sulfur impurities that could lead to the formation of acid rain, but it's also in limited supply. I just so happens that this past weekend was up in northern Wisconsin walking along a bog, and it's pretty early in the year for us, but this is kind of what that mossy peat moss, this is what that mossy substance looks like. And then I figured, since those guys were digging out that peat moss with their dog, my dog better be in a picture as well. Hi, Charlie. So what about coal? The guys, I hope, pretty good feel for that peat. Peat would maybe eventually become coal if we gave enough time and heat and pressure. But coal is really what we extract. The main use of coal, as you probably remember, is for generating electricity. And I'm guessing that your teacher got this kind of little mantra down for you about how we generate electricity from any combustion process. This coal is pulverized to increase the surface area. So I chop that coal up, I put it in a big furnace, I heat water, I make steam. That steam turns a turbine, and that is connected to a generator that transmits that electricity out through the grid. That's a lot of conversions. So remember the second law of thermodynamics. I am going from chemical energy, the potential energy stored in the chemical bonds of that hydrocarbon, to heat energy, to mechanical energy, spinning that turbine, to electrical energy. All of those conversions mean that at each conversion step, there's a loss of quality energy. I just have a lot of wasted energy. And so the more energy conversion steps I have, the less efficient my energy conversion process is. And that's really a drawback. There's a lot of good things about coal. There's a lot of coal. Remember why we use an energy resource. There's a lot of coal. It's really cheap. It's pretty easy to get out of the ground with dynamite and a lot of big trucks. And this process is, I mean, it's on a super large scale, but I'm just really taking this hunk of hydrocarbons and burning them. So it's pretty low tech, pretty easy, pretty cheap, and really vast supplies of coal. Remember that map. We don't even look for new coal deposits because there's so much that we know about that it's hundreds and hundreds of years. But it releases a lot of carbon dioxide when we burn it. One of the ways we can kind of get around that inefficiency of this process with all these energy conversions is the idea of cogeneration. This is just really maybe something you could use as a good solution. It's the idea that if I'm burning that coal and using all that heat to heat water to make steam to turn a turbine, that I can capture all of that excess heat and use it to heat my building. Co-generate. I'm using the energy that I've generated in kind of a dual way. So our next fossil fuel is natural gas. Natural gas is defined as the cleanest burning fossil fuel with a big asterisk by it, and we'll come back to that asterisk in a minute. Natural gas is, this kind of looks like that picture that we looked at the very beginning. It's a fossil fuel. It's usually found in a layer above oil because it's a gas, it's lighter. The natural gas itself is a mixture, but for our purposes, we can call methane and natural gas the same thing. I could say natural gas, methane, or CH4 if I were writing about this fossil fuel in an FRQ. I just want to point out, I don't need to know this. I don't need to know a lot of nitty gritty about the geology here. I just want to, in order to understand the big problems associated with extracting natural gas, I just have to understand that this natural gas is capped by this impervious layer. If you want to remember that it's a shale cap, that's awesome. Just so you get the idea that it's sort of trapped under this dense shale that's not going to let it through, that's not going to let it escape. So I have a layer of oil and I have a layer of natural gas. Remember that graph that showed us from wood to coal to oil to natural gas? For a while, when we first discovered oil, we knew that gas was there, but we didn't really have much use for it. We didn't have the technology to pressurize it and transport it and burn it efficiently. So as we figured that out, natural gas use is really on the rise. Why? Same thing that drives all of our energy decisions. It's very useful. Most of us may have a natural gas furnace for heating our home. There's a lot of it. We have good supplies. We have good domestic supplies. The cost of it right now is cheaper than coal. We hear a lot of talking points about why we're not using coal and coal miners aren't at work. Remember that our energy decisions are based on cost. And right now, natural gas is pretty easy to extract and it's cheaper per unit than coal. The reason we say natural gas is the cleanest burning fossil fuel is that it has less carbon dioxide emissions than other fossil fuels, less sulfur, less particulates. So relative to other fossil fuels, it's clean. But that's that big red asterisk. It's still a fossil fuel. We've looked at natural gas as a transition fuel to get us from fossil fuels into a more sustainable energy future. We still, even though it doesn't have as much CO2, it's still, when I combust the methane, remember we looked at that balanced equation, I still emit carbon dioxide when I combust a hydrocarbon. You probably remember hearing about hydraulic fracturing or fracking. This is the process to get the gas out of that, free it up, because we've got that really dense, impervious cap rock layer. And that's, again, even if you don't remember the name of it, I just want you to understand that in order to understand why we frack, you've got to understand that there's that impervious layer. This process of hydraulic fracturing produces large quantities of hazardous waste. And in addition to that, the methane, once I free it up through hydraulic fracturing, can now enter the atmosphere or the surrounding groundwater. And this is an image of a large hydraulic fracking operation in a northern forest. Understand that I can put a fracking well like this up anywhere. I could be driving in Denver, Colorado, and see in an urban area one fracking well. So although I can have big facilities like this, I can have small dispersed facilities as well. So let's go into a little bit more detail in review of that process of fracking, so that you can clearly describe some of the problems associated with it and maybe help us come up with some solutions. So the idea here is that I have this fracking fluid. It's a mix of water, sand, and chemicals that I pump down into the well. It's called hydraulic fracturing because that fracking fluid of water, sand, and chemicals is put under really high pressure. I have to crack that impervious rock layer in order to free up that methane. And they use this term propants here. That's the sand. Interestingly, we don't have methane or natural gas in Wisconsin, but we do have a lot of sand and gravel mining, and we have frack sand mining. We have a lot of sand that the fracking industry likes because of the nice grain size of it. So this propant is the sand. And once I put that under really high pressure and I fracture that rock, the purpose of the sand is just kind of hold those fractures open and let that methane seep up. And theoretically, all of that methane is captured by this well. However, in the process of fracturing that rock and allowing that methane to flow, some of that methane is going to get into the groundwater and contaminate it, or it can just enter the atmosphere. And methane is a greenhouse gas more potent than carbon dioxide. It has a higher global warming potential than carbon dioxide does. So while the fuel, when we burn it, may be a little bit cleaner than coal or oil, that methane fuel itself is escaping and entering the atmosphere. It's a little confusing because we're talking about methane as a greenhouse gas, but remember, it's a fuel in and of itself that I still have to then burn. And anytime I combust any hydrocarbon, I'm going to release carbon dioxide. The chemicals are the really big concern here. Notice that my diagram simply identifies it as various chemicals. The fracking industry has not been required to divulge much of the many of the ingredients. We know that there are persistent organic pollutants that are contained within some of that fracking fluid, but people that are exposed to some of those chemicals aren't really sure the exact nature of them. We have that contamination. We also use a great amount of water in that fracking fluid. And what happens then to all of that waste product is that it is stored in these toxic ponds. You may remember hearing about those, and we're going to come back and look at those waste ponds in a little bit as we look at another source of fuel. Let's just do a quick check-in here on the process of hydraulic fracturing or fracking. So we have a couple of different environmental problems there, and then a step in the nitrogen cycle just to throw you for a loop. And obviously the biggest concern here is groundwater contamination, because if I were going to turn this into an FRQ prompt, and I had to describe an environmental problem associated with fracking. I could talk about groundwater contamination. That's just identifying a problem. To describe it, I have to say how the groundwater is becoming contaminated. And remember, the methane can escape and contaminate the groundwater, or those big tailings ponds where all that waste is stored could leak if they're not lined and contaminate the groundwater. The next fossil fuel that we're going to look at are tar sands. And if natural gas is the cleanest fossil fuel, tar sands are the dirtiest fossil fuel. And in fact, that makes them pretty much the dirtiest fuel, doesn't it? So here's a picture of, and I'll show you this on a map in a minute. This is a picture of the area of old growth boreal forest. You know what the boreal forest is because you've reviewed that biome in Alberta, Canada, in northwestern Canada, where where these big deposits of oil sand are found. And this is what that area looks like after a tar sand project has come in. Obviously, the first thing that happened was large scale clear cutting of old growth boreal forest, hundreds of thousands of hectares of old growth boreal forest. The magnitude and scale of this destruction is almost hard for our human brain to kind of wrap around and visualize. And I think part of the problem is that this is happening in such a remote area of northern Canada that if you weren't an APE student, it may not be on your radar. So let's dig in a little bit more about what these tar sands are all about. It's a mixture of sand, clay, water, and a thick, viscous, kind of like molassesy sort of substance called bitumen, kind of like that coal. And it's mined. So if you remember, after I remove all the overburden, let's say I was going to do copper mining or gold mining, surface mining. After I remove all of the trees and all of the soil, and I take big equipment and dig down into that sand, this is kind of what that tar sand looks like. And I need to use chemicals and water to process and get the hydrocarbon out of that sand mixture. So the tailings ponds that are created, remember, we can have tailings ponds from the tailings from mineral mining, from mining of metallic minerals like copper, all of that waste rock. I can have tailing ponds from hydraulic fracturing, where I'm storing all of that toxic fluid, all of that fracking fluid. And I can have tailing ponds from the process of extracting and getting the hydrocarbons out of tar sand. And I'll just try to give you a minute to kind of orient yourself to this image from 1984 and 2011 up in Alberta, Canada, where these tailings ponds are located. So again, this image is just kind of to scale. It's in a little bit closer. And then I took an image just yesterday. So I'm going to show you that one. Again, I don't think we can even wrap our brains around how vast the destruction is of the forest and the massive nature of these tailings ponds. They are now holding 1 trillion liters of toxic waste. And that waste contains a lot of different heavy metals that can biomagnify in the food chain. So many of the indigenous people that rely on fish, for example, or caribou in their diet are getting very high concentrations of these heavy metals from contamination of their water supply by these tailings ponds. This is a Google Earth image that I took just yesterday. So just to orient ourselves, this part right here of the current Google Earth image is this area that you're looking at. I think you can kind of see how that matches up. So since 2011, we have doubled the production of that, and all of these are massive tailings ponds. This is what one of those tailings ponds looks like, and this is a highway with trucks that are bringing all of that waste to those tailings ponds. So it's something that should be of concern to us as we look at how energy decisions are made and the choices that we make and what kind of influence we can have on those. Let's take a look at, I'm going to walk you through a guided practice question as we look at the idea of a pipeline for transporting oil. You may have heard of the Keystone Pipeline. We have the original Keystone Pipeline, and we're going to in a minute talk about why we would have to transport that oil. Oh, here's where the Alberta tar sands are, in this big area up here. So again, the vast nature of them, it's really hard for us to visualize because this is such a remote area of just pure pristine boreal forest, not a lot of development. So the reason I would want to transport that oil via pipeline is to get it to a refinery. And we're going to look at refineries and review that in a minute. But you may have heard of the controversy. And I think in terms of pipelines, there's kind of two reasons that people have a problem with the pipeline. Number one, it's the pipeline itself, that I'm transporting oil underground. I think most of that pipeline's buried, but this is going right above the Oglala Aquifer. That is the major source of water for both municipal, agriculture, and industrial use for a large part of our country. A lot of the pipeline would go through private land, and there are people that may not want a pipeline transporting oil below their land. Maybe it will impact the value of their land, and the company maybe doesn't have a very good track record of leaks or breaks in that pipeline, and the ability to get to that pipeline and quickly repair it as all of that oil is leaking out onto somebody's land. I think one of the other big concerns about the pipeline in respect to the tar sand oil is that people feel that if the pipeline is built, it commits us to using the dirtiest fuel on the planet. That oil isn't going anywhere. If at some point in the future we are so desperate for oil that we need to extract that, it's always going to be there. So I'm going to give you a second to relate this to that beautiful boreal forest and tundra ecosystem that we were looking at, because whether I'm talking about the Keystone Pipeline to transport tar sand oil, or a pipeline that's going to transport oil from the Arctic National Wildlife Refuge, it's much of this oil exists in these fragile ecosystems of the tundra. So I'm going to give you a second to take a look at this question and see if you can describe two characteristics of Arctic tundra that make it fragile, and explain how those make it susceptible to damage. As we look at the responses here, they've divided them up into kind of biological, climate related, and physical. And I think one of the big ideas is that all chemical reactions happen slower in cold, dry conditions. So just the nature of this tundra environment means that rates of decomposition and recovery are very slow. The ecosystem is fragile because it's going to take a long time to repair itself if there's any damage to it. It talks about the permafrost and that soil being very shallow and nutrient poor. And again, the long amount of time it would take for it to recover if there were oil that presented that damaged the ecosystem. Next, let's take a look at tar sands in terms of other problems. The old growth boreal forest is being removed on a massive scale. Describe two environmental consequences other than those related to boreal forest habitat loss that result from the extraction of bitumen or the transportation of synthetic oil to customers. I'll give you a minute to look at this one as well. Two environmental consequences other than loss of boreal forest. Could be the extraction or the transport of that synthetic oil. Well, hopefully a couple of the things that you talked about were release of things like NOx and SOx and particulates. We're going to review those in air pollution later in the week. All of the mining waste that has to be stored, those toxic tailing ponds, the ability of that oil to spill or leak during transport through a pipeline, contamination of surface or groundwater. Here they talked about habitat fragmentation from the pipeline. So it wasn't the clear cut to get at the oil sands to begin with, the tar sands to begin with, but the idea that there's even habitat destruction in the construction of the pipeline. So lots of different potential consequences because tar sands are the dirtiest fuel on the planet. So remember I said that we had to transport that tar sand oil down to the Gulf of Mexico region, which is where the refineries are located. So the next concept that we're going to take a look at is what I do with oil to make it into a useful product, because we don't use crude oil in and of itself for anything. We first have to refine it, purify it. It's called fractional distillation or just distillation. And it's based on the fact that all of these different components mixed in that black unky crude oil, they all have different boiling points. So I have things that are gases at room temperature, liquids at room temperature, thick liquids. And then I get down to things that are actually solids at room temperature that have very high boiling points. And a couple of things I want to point out here. One of the most desirable fractions or components of this mixture of crude oil are these kind of low to medium length hydrocarbon chains like octane, the major component of gasoline. Petroleum engineers might take some slightly longer hydrocarbons and modify them in order to make them the right components. For the gasoline, for the fuel I put in my vehicle. So I have jet fuel, I have diesel fuel, I have paraffin wax, I get petrochemicals. That's another big component of this. All of these these carbons that I use to make synthetic compounds that include everything from pesticides to plastics to pharmaceuticals. Anytime I make a synthetic fiber, my dress here is a synthetic fiber. This is a rayon. This is a polyester that's made from crude oil. But they fraction it off into these separate components and then turn that into these synthetic fibers. So we get a lot of different compounds from crude oil, but I have to transport that to a refinery, and they're always located near a big source of water because guess what? We need a lot of water to purify or refine that oil. Let's do a little check for understanding here. Which of the following scenarios is an example of cogeneration? I almost said coevolution. Cogeneration. Got a couple of different things there that look at energy that if you didn't know could look like a reasonable term. Remember, it's using that sort of waste heat from the steam to actually heat a building. Extraction of natural gas by fracking is most likely to result in which of the following environmental problems? That question looks kind of familiar. Groundwater contamination. And that wraps it up for our first lecture on energy. So let's kind of take a look at what all we covered today. We looked at the difference between renewable and non-renewable energy resources. Make sure to have some good descriptive terms in your notes for that. We looked at how energy resources aren't evenly distributed between developed and developing countries, either the distribution or the use of them. The distribution is determined by geologic processes. The use is determined, how much we use per capita is determined by how industrialized we are, how affluent we are. We looked at all of these different fuel resources, from wood to peat to coal, natural gas, crude oil, and the idea of cogeneration. And then we look specifically at fossil fuels, at some characteristics of them. Remember, we reviewed that combustion reaction. We looked at the process of heating water to make steam to turn a turbine and generate electricity. And we looked at the various methods by which we extract fossil fuels, including hydraulic fracturing. And I think we really focused on these skills: describe patterns of energy consumption, explain why certain resources are located where they are, and justify the use of resources based on ecological, human health, and economic factors. So here is the reminder of the task verbs that you're going to see on your exam, all except calculate. You will not be required to calculate on the exam. And here's your homework that has to do with natural gas from rock, and hydraulic fracturing in the Marcellus Shale region of the eastern United States. So you're going to do that for homework, and check it with Dr. Sewell tomorrow, where you're going to talk about renewable sources of energy. So thanks for watching. Remember to, as you're going through and answering questions, keep in mind how you're organizing your notes and how they're going to benefit you on your national exam. Good to see you guys. Have a great day. Catch you next time.